Today we are discussing about a new experiment, hydrogen spectra and determination of rydberg constant. The aim of the experiment is to determine the wavelength of visible line in Balmer series of atomic hydrogen and to determine the value of rydberg constant. Hydrogen tube contain deuterium gas as an isotope of hydrogen. The gas is filled and pressure inside the tube is restricted to 0.5 to 10 millimeter of mercury. When high voltage is applied, the atoms are excited to higher orbit. There will be thousands of atoms inside the tube. Few of them will be pushed to n is equal to 3, n is equal to 4 and n is equal to 5. The emission spectra of atomic hydrogen has been divided into a number of spectral series with wavelength given by Rydberg formula. These observed spectral lines are due to the electron making a transition between two energy levels in an atom. The spectrum consists of many lines, but only 4 of them have wavelength within the visible region. All others are in UV or IR region. According to Born's theory of atom, E is equal to hc by lambda, where the wave number nu bar equal to 1 by lambda, which is equal to RH into 1 by n1 minus 1 by n2. So we have 1 by lambda is equal to RH into 1 by n1 minus 1 by n2. From this, RH is equal to 1 by lambda divided by 1 by n1 minus 1 by n2, where RH is the Rydberg constant. In here, n1 and n2 are the principal quantum number of electron, where n1 is less than n2. A series in the IR region of the spectrum is the Fashion, bracket and Piffand with n2 is equal to 3, 4 and 5. Here we are considering the Balmer series. n1 equal to 2, which is in the visible region. The individual lines in the Balmer series are H alpha, H beta, H gamma and H theta. In here we can only observe H alpha, H beta, H gamma. At normal incident, we have sin theta is equal to n lambda, where theta is the angle of diffraction, lambda is the wavelength of light, n is the number of lines per meter of grating, and small n is the order of the spectrum. For first order spectrum, n equal to 1, that is small n equal to 1. So capital N is equal to sin theta by lambda, where that lambda is equal to sin theta by n. The emission spectrum of atomic hydrogen has been divided into a number of spectral lines with wavelengths given by the Rydberg formula. These observed spectral lines are due to the electron making transition between two energy levels in an atom. A continuous color variation from violet to red is observed when a white light is passed through a prism or a grating, which is called a continuous spectrum. If colored lights such as neon, argon, etc. are used to illuminate the objective of a spectrum and grating through eyepiece, colored lines are seen. The colored lines are called spectra. The series of emission spectrum are Lyman series, which include light emitted by transition of electron from n2 is always greater than 1. Lyman series occur at the UV region. Using the equation 1 by lambda is equal to RH into 1 by n1 minus 1 by n2, we can find out the corresponding lambda values, and also from that we can calculate the RH value. RH is equal to 1 by lambda into 1 by n1 minus 1 by n2. This is the experimental setup for doing hydrogen spectra, and first we are standardizing. The preliminary adjustment of the spectrometer is done. That is, set the reading of vernier at 180. Now the telescope is turned without disturbing the prism table so that the vernier read 90 degree. Clamp the telescope. Rotate the prism table so that the reflected image on the slit by grating coincide with the crosswire. Again from the prism table, rotate by a 45 degree from this position in such a way that the ruled surface of the grating is forward. The telescope on the rotation in a line of collimator. Now the grating is in a normal incident condition. Rotate the telescope to set the crosswire on the first spectral lines, which lies in the blue, violet, and note the reading. Repeat this for the other spectral lines on the left and right side. The difference give help to calculate the wavelength using the relation lambda is equal to sine theta by n. The Rydberg constant can be also be calculated by using this method. For hydrogen spectra, we are using the hydrogen spectra. The intensity is controlled by a box. Using the box, we can after doing the experiment with mercury vapor lamp, after standardizing, we replace the mercury vapor lamp with the hydrogen spectrum with the by twisting the knob in the increasing direction of intensity. At a particular intensity, we can see the spectral lines very sharply and clearly. In the spectral lines, H alpha is represented by red line, H beta is represented by blue green line, H gamma is represented by violet line. Taking the values of H alpha, H beta, H gamma, we get the corresponding angle corresponding to the spectral lines. By using this angle, we can calculate. By using this theta value, we can calculate the corresponding lambda value. For that, first we standardize the green light using the mercury line. From that, we have lambda g is equal to 5461 into 10 raised to 10 meter. By using the equation lambda is equal to sine theta by n. From that, n is equal to sine theta by lambda. We get the corresponding value of n. In here, we get approximately 6000 lines per millimeter. Using this n value, we calculate the lambda for H alpha, H beta, and H gamma. Correspondingly, using the equation lambda alpha is equal to sine theta by capital N, lambda beta is equal to sine theta by n, lambda gamma is equal to sine theta by n. By using this three equations, we find out the corresponding wavelength of alpha, beta, and gamma lines. So by using the Rydberg formula, RH is equal to 1 by lambda into 1 by n1 minus 1 by n2 is done. In here, n1 is equal to 2 and n2 is equal to 3 for H alpha, n2 is equal to 4 for H beta, n2 is equal to 5 for H gamma. From by using this equation, R is equal to 1 by lambda divided by 1 by n1 minus 1 by n2, we can find out the Rydberg constant. So the result obtained by this experiment is the value of Rydberg constant. The standard value of Rydberg constant is 1.097 into 10 raised to 7. We get this almost same value using this experimental setup. Thank you. So, by concluding, we have discussed about the hydrogen spectrum and determination of Rydberg constant. Here we actually want to find the Rydberg constant by finding the lambda alpha, lambda, beta, lambda, gamma, and considering the Balmer series, that is the visible series, we find the using the Rydberg formula, we find the corresponding Rydberg constant. Thank you.